In part 2 of today's lecture, we're going to talk about a particular kind of situation where neural networks can make mistakes called adversarial examples. So in part 1, we mostly talked about natural perturbations to the images, correlations, distributional shift, things like that. In this part, we're going to talk about some unnatural perturbations that both have implications for the security of machine learning models and also can teach us a little bit about how neural nets do or don't generalize. So first, let's just talk about what adversarial examples are. It's something that many of you might have heard about before, but I think it's important for us to get the facts straight. So adversarial examples are a particularly vivid illustration of how learned models may or may not generalize correctly. So here is a classic picture of an adversarial example. You have a photograph on the left. The original photograph is classified as a panda with kind of medium confidence, 57.7% confidence. Then we take this special pattern, multiply by a small magnitude, 0.007, add it to the picture of a panda, and we get a new picture that is visually very, very hard to distinguish from the original, and it is classified as a gibbon with 99.3% confidence. Okay, that's maybe a little worrying. The special pattern that we added, it's not random noise. I know it looks like random noise, but it's not. It's a very, very special pattern, specifically selected to fool the model. So it is called an adversarial example because that special pattern is chosen adversarially. So not just random noise won't do this. You need a very special choice of pattern. It is multiplied by a very small number. So small, in fact, that I think when you are viewing this on YouTube, probably the combination of the video compression in the video and the way that I made this slide, it probably makes the image on the left, the panda, and the image on the right, the gibbon, actually visually identical to you. Not merely similar, but actually identical. The images, they typically use 32-bit representation for values. Most computer monitors use 8-bit color for videos and images and things like that. So you're probably not actually seeing the perturbation at all in the image on the right. But for the neural network, it would be visible. Okay, that's a little uncomfortable. What's going on here? Well, what's going on is that very special patterns, almost imperceptible to people, or in this case, completely imperceptible, can change the model's classification drastically. They can turn it from sort of a medium confidence but correct panda classification to an extremely high confidence but incorrect gibbon classification. Why do we care about this? Okay, it's like kind of weird. Is it just an idle curiosity? Well, there are a couple of reasons. First, there is the very direct issue, which is that this is a potential way to attack learned classifiers. Okay, chances are there's not much incentive for pandas in the wild to dress themselves up to look like gibbons, but there is quite a lot of incentive. For example, if you have a classifier that is detecting credit card fraud for a fraudster to disguise their transaction in some way so as to fool your classifier. There is potentially a lot of incentive for someone who's trying to evade an automated surveillance tool to modify their appearance somehow, or a lot of incentive for someone uploading, let's say, copyrighted material to a website to subtly modify that material so that it is not classified as being copyrighted, right? So there's a lot of these scenarios where the actual security implications of this attack are very salient, where someone would actually want their input to be misclassified by your model. And then there is perhaps the bigger indirect issue, which is that if neural nets can make such mistakes, if you can show them a picture that looks almost indistinguishable from the original, in fact visually distinguishable to humans but is labeled incorrectly, maybe this implies some very strange things about how these networks do or don't generalize. And maybe if we can think about those things carefully, if we can figure out why this happens, maybe we can build better neural networks that generalize more effectively. Okay, So we're going to discuss adversarial examples in great detail in this lecture. Both part 2 and part 3. We'll talk about them, why they happen, where they happen, how we can make them happen, how we can prevent them from happening. But before we get into all the details, which we will discuss at length, let's just get the full picture first. Let's just get some facts down on this page that help us understand what adversarial examples actually are and when we should be thinking about them. Okay, so first, it's not just gibbons. So adversarial examples, these special patterns that you add to a picture, if chosen properly, can turn just about anything into anything else with enough effort. It's not all equally easy, but in general, there is a lot that you can do with adversarial examples, in the sense that there are many different classes you can turn into many other classes for many different kinds of networks in many different kinds of situations. It is not easy to defend against adversarial examples. There are many ways to attempt to modify your network to make them less susceptible, but as of today, as of April 2021, nothing that we know of provides a bulletproof defense to adversarial examples in all cases. So there are definitely defenses, there are definitely ways to reduce their effectiveness, but we do not know of anything that solves them completely. Adversarial examples can transfer across networks. This was a very surprising finding when it came about, but it is not a very, very special property of a particular network. You can create an adversarial example that will fool AlexNet, and it will also fool ResNet. Not always. Not all adversarial examples transfer, but in many cases they do. Adversarial examples can work in the real world. They're not just special and very precise pixel patterns. What is this image? It's a 45-mile-an-hour speed limit. The photograph was not altered. The photograph was just taken with a regular handheld camera. What was altered is the sign. That bit of smudge on the sign that looks kind of like dirt was actually selected in a very careful way so that photographs of the sign, normal, natural, unaltered photographs from many different distances and angles, would all be consistently classified as a 45-mile-an-hour speed limit sign. Adversarial examples are not specific to artificial neural networks. Virtually all learned models are susceptible to adversarial examples. So it is not some weird pathological property of deep nets. It's not a weird pathological property of any particular deep net. Almost all learned models that we know of can be attacked with adversarial examples, and not just artificial ones, natural ones too. So there are adversarial examples for your brain, which is also a type of learned model. Okay, so let's talk about some of these facts in a little more detail. I'll start with the question of whether adversarial examples are specific to deep networks. This question is important because it will later on shed some light on why adversarial examples might happen, which is still not a question that we can answer definitively, but we have a few hints. And also it helps us make practical real-world decisions. Like, for example, someone might think that, well, maybe if it's a problem only with deep nets, if I want a really secure machine learning system, I should avoid using deep nets. And that's generally not the case. So this is an example from a talk by Ian Goodfellow. I'm going to use a lot of examples from Ian's work in this lecture. This is an experiment that Ian did attacking a linear model. I believe this was actually a logistic regression model. So what this picture is showing is you start off with a handwritten digit of a 9, and then Ian was going to alter this digit in subtle ways. Here the perturbations are a little bit more perceptible. You can see that the background does change a little bit. So he's going to alter in subtle ways to get it to be classified by all other classes, 0, 1, 2, 3, 4, 5, 6, 7, and 8, in order, by a linear classifier. In this case, it's a logistic regression classifier. And whenever you see a yellow square, that means that that digit has now been classified by its corresponding label. So here, this 9 now is classified as a 0 with 90% confidence. Then in the second row, It's not now starts getting altered from there until it's classified as a 1 with 90% confidence. Then in the third row, it's classified as a 3, then a 4, then a 5, etc., etc., etc. And then all the way in the bottom right, it's classified as a 9 again. So this linear classifier could be persuaded to classify this digit with any of the possible 10 classes without actually altering which class it really is. Adversarial examples appear to be a general phenomenon for most learned models and all high-capacity models that we know of. Okay. So at that point, another question that we might want to answer is whether adversarial examples are due to some kind of overfitting. This is also an example that I'm borrowing from Ian's work. So one possible hypothesis for why such really tiny perturbations can seemingly alter the class of an image is that when you have a very large model, when you overfit to your data, you might get all these like crags and crevices in the decision boundary, almost like, if you imagine, if you take two rational numbers, there are always infinitely many irrational numbers between them, so you could sort of say between every pair of pandas, there's infinitely many gibbons. Maybe it's something like that, where if you have a really, really nasty function with lots of kind of wavy stuff in the decision boundary, maybe between any two images of a class, there will be many other images of other classes kind of hiding there. So the overfitting hypothesis is that because neural nets have a huge number of parameters, maybe they tend to overfit, making it easy to find inputs that produce crazy outputs. So the implication of this hypothesis is that, well, to fix adversarial examples, you should not use high-capacity models. You should use smaller, simpler models. So the mental model for this kind of hypothesis is, let's say that we have these two classes, and we would like a really nice, clean decision boundary like this. If we train a neural net, maybe we get like a really crazy decision boundary like this, which does very well in training data, and maybe even does really well in test data because these little crazy bits are really, really thin, like that bit on the left. But if you actually optimize for an image, you can easily find one that is in the wrong region. So that's kind of the overfitting hypothesis. Okay? It's a sensible hypothesis if we put together the fact that adversarial examples tend to require very, very small perturbations, and they tend to be pretty problematic with deep nets. However, most evidence that we have today suggests that this is false. It suggests that this is not what is happening. Now, admittedly, this evidence is a little circumstantial, but if this were true, we would expect different models to have very different adversarial examples. See, overfitting corresponds to high variance. High variance means that for different data from the same distribution, or similarly for different models, you would expect decision boundaries to be different. They would all be about equally incorrect, but they would be different. That's what high variance means, and we know that overfitting means high variance. And that is not what we actually see in practice. In practice, we see that adversarial examples often transfer between different networks. So it does not appear that adversarial examples are actually symptomatic of high variance. In fact, the variance for them actually seems surprisingly low, considering how arbitrary they are. So this is pretty conclusively not the case. Okay, another point. If this were true, we would expect low-capacity models, like linear models, not to have this issue. And again, this seems to not be the case. Low-capacity models also have adversarial examples. And lastly, if this were true, we would expect highly nonlinear decision boundaries around adversarial examples. So if the decision boundaries really looked bizarre like this, we ought to be able to construct some visualization and see that. And generally we can't. And I'll talk about that in a second. So this is an important point to consider because the overfitting hypothesis is usually the first thing that jumps to mind for people when they hear about adversarial examples. Because it actually is fairly natural to think that way, because if a small perturbation to a particular point can result in it being classified as a different label, that might suggest your decision boundary passes close to that point, and decision boundaries that skirt too close to the data, at least in low dimensions, are very much in line with our intuition about what overfitting looks like. The issue here is really that our intuition for low-dimensional spaces doesn't give us a clear picture of what happens in high-dimensional spaces. A very different hypothesis, which we can call the linear models hypothesis, says that because neural networks and many other models tend to be locally almost linear, they extrapolate in somewhat counterintuitive ways when moving away from the data, where the word away has a slightly counterintuitive meaning in high dimensions. So this hypothesis may seem a little far-fetched, but I'm going to show you some evidence that supports that this might be true. And again, this is mostly based on some work by Ian Goodfellow. So let's look at a different example. And this example I chose somewhat carefully to illustrate this hypothesis. So here I intentionally chose the data so that it lies on a kind of low-dimensional manifold. And this is a very reasonable thing to consider because natural images, for instance, lie on a very low-dimensional manifold in the space of n by n arrays, right? So if you consider all random n by n images, most of them are not going to look like natural images. Natural images have very special structure. They tend to have lots of low frequencies separated by edges, not the kind of thing that you get if you just generate random noise. So if you want kind of a mental model for this, you could imagine a really big space that corresponds to all possible images one could generate. Kind of think of it as a volume. And then you could imagine a thin sheet, a thin wavy sheet in that space, representing the set of all images that are realistic images. And that's why in this example I chose, even though I have only 2 dimensions, I chose to make this manifold of realistic data mostly follow one of the dimensions. There's still some variation in the other dimension, but not nearly as much. So when I fit a locally linear, or in this case a globally linear classifier, I might get a decision boundary that looks something like this. This is a pretty good decision boundary in the sense that it separates the 2 classes very cleanly. But you'll notice that the decision boundary, of course, is in both dimensions. That the decision boundary doesn't realize that there's this low-dimensional manifold where the data lies, and it has a slope along the other dimension as well. And what that means is that if we generate another example by taking the irrelevant dimension, the vertical one, and moving just a little bit along that irrelevant dimension, we can actually produce an example that will be classified incorrectly. Now this picture is still pretty deceptive because here I only have 2 dimensions. In reality, if you have an image with, let's say, 1,000,000 pixels, the number of relevant and irrelevant directions might be very, very large. So here, because I have only 2 dimensions, I need to move pretty far along the irrelevant dimension to get an incorrect classification. But if I had, let's say, 100,000 of these irrelevant dimensions, maybe I wouldn't need to travel so far along any one of them. I could travel a short distance along each of them and get an incorrect classification. And that's why, for those adversarial examples, they could, perhaps this is why they could get away with imperceptibly small perturbations. Okay, so why would large neural nets look linear like this? Right, because the whole point of neural nets is that they are nonlinear functions, right? Well, rectified linear units are piecewise linear, so you could imagine the composition of many rectified linear units will consist of a large number of linear slabs. And the number of those linear slabs might be very large. It might in fact increase exponentially as you increase the number of layers. But locally, it would still be very linear. You could say, well, okay, why don't we just not use ReLUs? Well, if we use other nonlinear units like sigmoids, they still tend to operate best when they're in that middle regime, right? Because they saturate on the tails. So the way that sigmoids are typically used, they also stay in a region where they're locally quite linear. So a lot of the models that we actually use, they do actually look locally linear because of their structure. And you could say that it's actually more than skin deep. You could say that we use these kinds of models because they're easy to train. And models that are locally linear like this tend to be easier to train because their gradients are well behaved. A gradient at some level is a linear approximation to a model. So if you have a model that looks locally linear, then a gradient would be a good approximation to it. So you would expect that it would be easy to optimize with gradients. That's in fact why people switch from sigmoids to rectified linear units, because they are more linear and therefore easier to optimize. So it's maybe not an accident that these models look locally linear. It's actually one of the things that makes them easier to train. This hypothesis is consistent with the transferability of adversarial examples, because it would really say that the problem is almost more of an underfitting problem. And you would expect that to correspond to low variance, which means that you would expect those adversarial examples to transfer across small variations in the training set and across some variability in the model. Reducing overfitting doesn't seem to fix the adversarial examples problem, which is again consistent with this hypothesis. And there's a little bit more evidence that this kind of linearity stuff might be what's really going on. Here's an experiment. It's a slightly strange experiment. We're going to take a picture of a white car on a red background. So the pictures on the left show what's going on. We're going to alter this picture. We're going to pick a direction in image space. And then we're going to add multiples of that direction. So the direction is basically a vector. It's another image, a modification to the original white car on a red background image. And we're going to add 0 times that vector, or 1 times that vector, or 2 times that vector, or 10 times that vector, or also negative values. So if you look at the images here on the left, they're a little hard to see on the slide, but the ones that are highlighted in yellow, those are correctly classified as automobile. And the one on the right end of that row, that's the original image. So if you go 1 to the left of that, that is the original picture minus epsilon, which is your vector, times 1. And then the one to the left of that is minus epsilon times 2, and so on. In the graph, what you're seeing is the values that go into the softmax. So these are not the probabilities of the network outputs, it's actually the logits, the ones right before the softmax. And you can see that in that little region close to 0, that's where the original image lies, the shape of the curves for the different classes is pretty complicated, and there's a little bump for car right around its 0 where it's classified correctly. But as you modify the image more and more in one direction or in the other direction, you can see that the logits eventually flatten out, and then from there they start expanding linearly. So somewhat bizarrely, the frog class actually becomes the most likely for large perturbations both to the left and to the right. And it's not because the network actually thinks a frog is very likely, it's just because it's extrapolating linearly far away from that image. And the slope of the frog class just happens to be larger, so if you go far enough, eventually the most likely thing is the frog. This is not what you would expect from a model that, for example, has calibrated uncertainty. You would expect as the image gets more bizarre, maybe all of the class logits should become similar, reflecting the network's uncertainty about what the class is. But here you can see the network is extrapolating linearly. Here's another example. This is a little bit more difficult to understand, but I'll do my best to describe what this is visualizing. Here, the authors of this study, this is from Ian Goodfellow, David Ward-Farley, and Nicolas Pepernot, the researchers constructed an adversarial direction for a large set of CFAR10 images. So every box in that funny, colorful quilt on the right represents a different CFAR10 image. And for each of those images, what they're plotting in each of those boxes is the classification outputted by a deep network as that image is varied along 2 directions. So you can sort of think of each of those little boxes in that quilt as a little plot of a 2-dimensional embedding of images, where the center of that point is the original image. As you go right and left, you're actually moving along an adversarially chosen direction. So the horizontal, the left to right direction is chosen intentionally so that the network will maximally change its classification along that direction. It's actually calculated by taking the derivative of the class label with respect to the image. The vertical direction is just a random direction. So why are they doing this? Well, they're trying to understand, does the image classification change more along random directions versus along adversarial directions? Of course, the adversarial directions will change more, but how much? And the reason that this kind of visualization is useful for us to understand the linearity hypothesis is that we would expect if the problem was due to overfitting, if the problem was due to the decision boundary being some really complicated thing, we would expect to see that really complicated thing in these plots. Basically, this is a two-dimensional projection of the image space. So if we were getting overfitting, if we were getting something like this picture, we would basically expect to see stuff like this pop up in each of those cells of that quilt. Okay? But that's not actually what we're seeing. We're seeing that in most of these cases, the decision boundary is pretty straight, and it's pretty well aligned with the adversarial direction. So basically what you're seeing in most of those cells is a vertical line, where as you cross that vertical line in one direction, you get an incorrect label. So white is the correct label, any other color is a different label. Basically, if you go far enough to the right, you get an incorrect label. And it's always on the right, it's never on the left. So you really have to go in the adversarial direction. It's not like the network is super sensitive in this direction in general, it actually only goes one way. You very occasionally see some more complexity. Like for example, the third image in the second row has a kind of a funny shape around the top and bottom. But in most cases, the decision boundary is basically linear. So this is not what you would expect to see if what you were getting was massive overfitting. Okay. So there's not much variation orthogonal to the adversarial direction. It's up and down in this plot. And you have a clean shift on one side for the adversarial direction, suggesting a mostly linear decision boundary. Okay, so that maybe helps us understand a little bit where these adversarial examples are coming from. Let's look at a few more kind of vivid illustrative examples of this kind of stuff in action. So in the picture on the left, this is from a paper called Robust Physical World Attacks on Deep Learning Visual Classification. Here, the authors are showing natural photographs of various traffic signs that are all classified as 45-mile-an-hour speed limit signs, photographed from at different angles and from different directions. And the numbers at the bottom show the success rate of these attacks. And you can see that the attacks range from putting some patterns on the sign that look a little bit like dirt to putting even like some stickers that look like maybe graffiti art. So there's a variety of ways to construct these attacks that all appear to work decently well. In the images on the right, there's an even more extreme example. This is from a paper called Synthesizing Robust Adversarial Examples, where the authors actually 3D printed physical objects that are reliably classified as a different class from different angles. So in the top you see a turtle. This is an actual physical object that these people made. This is not a rendering, this is an actual physical thing. And all of these turtles are classified as either a gun, a rifle, or as something else. So the black ones, the ones with the black outline, are classified as something else. The ones with the red outline are classified as a rifle. And none of them are classified as a turtle. The example below that, it's a baseball. This one is not quite as powerful, but in many of these cases, the ones with the red outline is classified as an espresso. The ones with the black outline are classified as something else, and a few of them are actually correctly classified as a baseball. And you can kind of, with a baseball, you can kind of guess why. If you look at some of them, it looks a little bit like coffee with some bubbles in it. So, at this scale, if you want this level of robustness, some of the features do look a little suggestive, but they're not ones that a person would likely mistake. So let's talk about things that a person might mistake. Are there such things as human adversarial examples? Well, the lame answer that I could give you is, of course there are. They're called optical illusions. So in this picture, for example, the squares are arranged into concentric circles, not spirals. I know they look like spirals. They're not spirals. They're concentric circles, not spirals, even though they look like them. The reason they look like spirals is because the squares are tilted in just the right way to create the illusion that these are spirals. And of course, there are lots and lots of different illusions that we know humans to be susceptible to. Now, one might argue that maybe an illusion is not quite the same as an adversarial example in the sense that an illusion actually plays to our brain's prior beliefs about how shapes work, and maybe that's a little bit different. There is actually work on studying real human adversarial examples. There's a paper called Adversarial Examples that fool both computer vision and time-limited humans. These are actually pictures that fool your brain in the same way they fool neural nets. I'm going to show you one such picture. I'm going to show you this picture, and I want you to guess what the class of the picture is. It's going to be either a cat or a dog, so binary classification. When I show you the picture, guess as quickly as you can. Actually say it out loud. Say cat or dog. Say it out loud to keep yourself honest. So I'm going to show you the picture in 3, 2, 1. Okay. Remember your guess. So here's the original. All right. Now, some of you might be thinking, well, okay, maybe I'm messing with you, right? So the picture on the right is, in fact, constructed using an automated technique for synthesizing adversarial examples. It does, in fact, reliably fool humans. The criticism that you might mention is that, well, maybe this picture has been altered so much that it actually really is a picture of a dog and not a cat. So the correct class is cat. It looks very much like a dog. But maybe that's because it really is now a picture of a dog. There's a little bit of a philosophical conundrum here, which is we actually don't know. If you're a person looking at this, you're going to see a dog. What's the true class? How do we measure that? We don't know. So maybe it's an adversarial example. Maybe it's really changing the class of the picture. The actual experiments, which are a little bit more verifiable, had to do with time-limited humans. So in the actual examples, humans were shown a pattern for a small period of time, less than 100 milliseconds. And they were asked to guess what the class of that image was. For most of these examples, if humans are allowed to look at them for an extended period of time, they will actually be able to figure out the class correctly. But if they're only given less than 100 milliseconds, they can pretty often get the class wrong. So what you're seeing in the top there under A, these are the actual perturbations that won't fool you when you're looking at the picture for an extended period of time, but they will actually fool time-limited humans. So for example, the picture in the second row, that dog, the second column is subtly modified. So subtly you might not actually see it very clearly on this slide to fool humans. Okay, so this is all well and good. What does this all have to do with generalization? Well, the linear hypothesis is relevant not just for adversarial examples, but really for understanding how deep nets do or don't generalize. When you train a model to classify cats versus dogs, it's not actually learning what cats and dogs look like. It's learning about the patterns in your data set. And from there, it'll extrapolate, potentially in weird ways. So it's going to be a good horse. Put another way, adversarial examples, they might not reflect bugs. They might actually reflect features of your learning algorithm. Just like the snow in the background for the wolf is actually a valid cue for the problem that you set for your neural net, in the same way, these directions that seemingly can be used to exploit and produce adversarial examples might actually represent useful patterns that the network is paying attention to because they help it get the right answer on the training set. In fact, this might literally be true. There's a very nice paper by Andrew Ilias et al. Called Adversarial Examples Are Not Bugs, They Are Features, that basically argues this hypothesis. The basic idea here is that maybe neural nets pay attention to these adversarial directions because it actually helps them get the right answer on the training data. And it's not overfitting. It's actually the right thing to do to get the right answer, to basically answer the question that you were posing for them. And it just happens to make them vulnerable to these adversarial attacks. That's not actually entirely surprising in the sense that any system that is tuned to be really, really optimal at a particular thing is likely to become less robust. Now, those of you that listening to this lecture that have a background in controls will find this very familiar. It's very well known that more optimal controllers tend to be less robust. In the same way, more optimal neural nets might be less robust to these kinds of perturbations because they're really, riding the knife edge of the classification boundary. They're really trying to find the most optimal way to get exactly the right answer on your training distribution. So to summarize, the neural nets generalize very well on test sets drawn from the same distribution as the training set. And they sometimes do this by being a smart horse, by picking up on patterns that allow them to get the right answer, but patterns that might not hold if the distribution changes. Like, for example, the snow and the grass in the background of the wolf. And it's not their fault. It's your fault. It's your fault for asking them the wrong question. They're often well-calibrated, not well-calibrated, especially on out-of-distribution inputs, which means that the probabilities that they produce might not reflect the real frequencies of those events, even when the most likely label is the correct label. A related but not the same problem is that we can almost always synthesize adversarial examples by modifying normal images to fool a neural network into producing an incorrect label. Adversarial examples are most likely not a symptom of overfitting. They are conserved across different models, and they affect low-capacity models just like they affect high-capacity models. And there's reason to believe that they're actually due to excessively linear or excessively simple models attempting to extrapolate, plus some amount of small distributional shift. They afflict humans, they afflict neural nets, they afflict logistic regression. Adversarial examples can be constructed as real-world objects, and they are very difficult to deal with. Okay. In the next portion of the lecture, I'm going to discuss the actual math and the actual algorithms we can use to construct these adversarial examples.